Hey everybody, welcome to a new episode of Integrated Circuits with Rashid. Sorry I'm bringing this episode a bit late. I think it's been 2 to 3 weeks. First I am in Ramadan, so then there are a couple of hobbies that I have, so I got really busy with those. Anyhow, I'll try to bring the next episode sooner, maybe once a week or once in 2 weeks. Um, Okay, and let's get started. We were discussing standard cells, and okay, I remember the last time we talked flip-flop. So my plan today is complete the flip-flop circuit and then go into the layout of MOS and layout of inverter or AND or NAND. After that, maybe look into how now standard cell library is formed, what kind of different views exist there. Timing and layout are the two most important views. So we can talk about those. Um, we'll see how much time we have and how much we cover in these 30 minutes, but let's get started. Okay, last time we looked into what is setup and hold time in flip-flop. Okay, let's look into the circuit a bit more to understand the functionality of flip-flop. How is it different than a latch? Okay, so if you remember in latch, we had one storage element and we were controlling the transparency of the latch or the state when it holds its previous value. It doesn't output doesn't change with respect to input. So in flip flop, there are two stages. There are two storage elements. So let's put the same circuit that we had. Okay, this. So if you remember, this was the circuit we had last time. I just want to make sure it's the same circuit. Okay, and this is control. Inverted clock comes here. So this is clock and this is our input. Okay, this is one. In flip-flop we have two stages. So let's create the same stage here. Okay, let's maybe bring a different color in it. Okay, let's try. These are our switches. This switch is for clock. This switch is also controlled through clock but have an inverter, so that when one is on, the other one is off. What's this number one? Okay, let's have a look at this circuit. Okay, yeah. Start with the for the clock. As you know, clock is the thing that times our whole digital circuit. So this is our clock. Let's start with when clock is 1. Okay, which is this time. Okay, when clock is maybe get let's get blue. This period. So when clock is 1, okay, since this inverter, this output will be 0. Okay, so this 1 means our NMOS is this NMOS is on and this one is disconnected. Okay, what's happening is now we are writing this input, okay, on to this point. So whatever is the input, and that goes the inverted output. So we are writing onto this node. Okay, Now let's see what's the state of the other element. Um, okay, I think we one other thing I missed that. Okay, the main clock that goes to the same this switch that is over here is an inverter version of this clock. So when this is 1, this is 0. When this is 0, this is off. When this is 0, this one is 1, and this one is on. Okay, so our first stage is in sampling. Okay, our second stage is holding. Okay, so whatever the previous value was here or here, those values are maintained, and while this stage is letting the input the output. So what's happening is during this stage, clock 1, during this stage we are keeping our, let's say we have data inputs. I'm saying there could have done a bit, but maybe it will be easier to explain with the data. Okay, not doing that now. Let's make it a little bigger. Okay, so this is data 1. This is input, so let's say data 1 or D1, be easier. So this is input, so this is our data 1 or D1, and output, let's say it was already a value, which let's call it data 2, and output, let's draw here. So clock 1, output stays at D2, input stays at D1, and so this value is written, this node over here is D1. Okay, as soon as we clock half cycle changes, so we go into the second half, clock becomes 0. As soon as clock becomes 0, let's see if I can draw on top of it. Sorry, there's too much stuff here. So let's clock is 0. Make it a bit more red. So this is 0 and this is 1. When this is 0, now this doesn't work. It's off. This is on. And this is 1. This is on. This is off. Now, what we are doing is now that this, let's draw it cleanly. So this is off. This is on. And in the next stage, this is on. This is happening now. The first circuit, which was sampling, now it's keeping the value, whatever value we stored before here. It's inverted and then inverted again. So that means this node maintains its previous value. However, when clock is 0, now this stage, or second stage, is letting whatever here go to the output. Okay, so as soon as we go into clock 0, and we see our output now changes to D1. Okay, this output. So you see that in flip-flop, okay, in, let's say, clock cycle was high, output doesn't change. Input was D1, output stayed at D2. As soon as we have a transition and we enter into second half, the output now, guess what the input was before, it was D1. So flip-flops that's why edge sensitive. output value changes when clock edge happens. Now you can take a look that this is where the change happen on fall edge of the clock. So it's fall edge flip-flop. Now some flip-flops can be, if you it depends on where you put this main inverter for the clock. So you can also make them transition in the other way, like data transfers when there is a rise edge of the clock and doesn't change when the fall edge of the clock. Okay, so hopefully that explains the functionality of flip-flop. Important here, if you think of setup and hold time. So what you want to do when you are in this cycle, for when the clock is 1 in this circuit, when this node is sampling the input value, and the second stage here is keeping the previous value. So pay attention to this one. So as soon as transition happens, okay, this will stop holding the input, or keeping the input, and immediately the second one will start taking what was here. So during that transition, you don't want to change the input. You whatever input you want to be have at the output after the edge, you don't want to change it during this transition period. First, because if you change your thing here, like let's say you put it here D3. Now this side will take, then the output will take immediately here D3. Okay, while we wanted to keep D1. So this time, before the sensitive edge of the flip-flop, where we need to keep the input data stable, is called setup time. And then also think of that the edge, after the edge, you also want to keep for a little while data stable, because see, this clock which I'm drawing here is ideal, but actually it's not ideal. So our clock will be some transition time, right? This is more like a realistic clock. It will take some time to change. And what you want to make sure while clock is changing, okay, and our circuits are sensitive to the value of the clock, we don't want to change anything. Just sometime before the flip-flop, before the sensitive edge, and sometime after the sensitive edge. So the time before is setup time. Time that you hold it after the edge is called hold time. Okay. So hopefully that explains flip-flop. We haven't looked into the layout, so let's talk about the layout a little bit. So how is MOS? I think I drawn this before. Our MOS circle, let's say NMOS. Oops. Okay, it has, let's think like that. It has an N plus region, 2 N plus region. One is drain, the other one is source. Depends which one is connected to ground. So ground one will be source. And at the bottom we have, this is a substrate. Okay, so that's substrate. And here we have silicon dioxide, and then we have the gate terminal here. So this point here has a dielectric here with silicon dioxide, and it acts as a capacitance. So eventually our current flows, let's say from drain to source like this. Okay, so this is in 2 dimension. Let's look into it in 3 dimension. So what we do is, oops, yeah, let's take a look like this. Okay. So this, the distance between, so let's say this is drain and this is source. Okay. The distance between drain and source, let me go with a different color, a better explanation. So this distance is the length of the transistor. Okay. And you know that there are different technologies. Okay. It's a 10 nanometer, it's 22 nanometer, 14 nanometer. And this is the length. It's 14 nanometers, it's a 14 nanometer technology. 10 nanometers is a 10 nanometer technology in simple forms. In actual transistor, when you go deep, then your effective length can be a little different than this length. But anyway, for simplicity, let's keep it like that. So this length is the technology node we talk about. And the other one, this side, or this side, this distance is the width of the transistor. The current through the transistor, we didn't go through the equations for current, but this current that passes through here, you can see that if this length is shorter, so this drain and source are closer to each other, there will be more pull of the current. The charge that moves per second will be a lot more. Okay. So the relationship is when L length goes down, current goes up. Okay. However, with the width, when you make this width bigger, and you have a, let's say you go on there, you have a much larger area that can keep the current flowing. So when width increases, current increases. Okay, so the equation is W over L. Typically, that be the constants for a given transistor. So what we do is, in the standard cell library, so we have different standard cells. We have inverter, we have buffer, we have AND, we have NAND, we have NOR, we have flip-flop, we have latch, and some others complex cells too. What we do is, in standard cell library, let's say it's our library. Okay, sorry. Stop this. So we have different shelves in our library. Okay. This is, let's say, inverter shelf. Okay. So we develop transistors with the different widths. Okay, we will have one, and let's say call inverter 1 with one value of width. We make another inverter with a bigger width, another one even more. So we have a variety of this inverter in a given library. Similarly, same thing with any NAND or any flip-flop. There are different versions of those cells, and each has a different width of the transistor. Now what happens as, let's look into power, performance, and area implication of different versions of inverters. But I do want to touch on one other thing. So this was the transistor that we are familiar with before, I guess, 22 nanometer Intel, or maybe the 40 nanometer was the first dry gate. But before, we were applying drain on this side, and we had a source from this side. Okay. Now, as we start decreasing the length of the transistor, so they started getting closer, right? The way we control, as I mentioned earlier on, that transistor is a switch. Better this switch is, better we will be able to transmit our information. And we need a good control over transistor. So when we want it on, it's on, and when we want it off, it's off. Okay. But what happened that as the transistor's length got smaller and smaller, okay, it was becoming hard to turn the transistor off completely. As I mentioned before, that there is the way we control over this region is we have polysilicon gate, and then we have dielectric silicon dioxide. Okay, this we make a capacitor here, and through the once we have a given voltage here, and this source is connected to ground, once we change the voltage on the gate, okay, this a strong capacitor is formed here through dielectric silicon dioxide, which pulls the current here. So as we increase the voltage, decrease the voltage, the intensity of the current goes up and down. So when we put a 0 volt, okay, this transistor is off completely. But as we made it this length smaller, it became very difficult to make this transistor off, that even when you have a 0 or close to 0, you still have some electron escaping. And we started making our silicon dioxide thickness smaller. It was like then smaller and smaller. Eventually, we really limited by the number of items in the silicon dioxide. So it was not possible to do more engineering of the silicon dioxide and still make it more controllable through this top structure. So what we did, I think at 14 nanometer or 22 nanometer, I'm forgetting right now where the actual transition happened, that since it was hard to control it through these two, and you wanted to get more control of this channel, this is where this current is flowing, what we did, we turned the gate into a little bit different structure. We said, okay, from the top we are controlling here. We want to control from this side and the back side. The back side there, let's say. So let's try it again. Okay. All right. So we started controlling. We put we say, okay, we on the back side, and on the side we surround this area on the 3 side, here, and the back side with the gate. So our gate now becomes like goes top, then comes down, and then comes here. Okay, so this is the modern transistor, this structure of gate that come. These are called fins, the FinFETs. So now we have control from 3 sides, so we have a better control of the channel area. So yeah, so that's the structure of MOS. Going back to where I was going before, as one second, let me look into. So let's look into power, performance, and area. as these are the main three main things that we want to optimize on a given circuit. Okay, let's say we have a restriction um, of a circuit that okay, we only have certain die area and we have to put all the functionality of a given SoC into that. So we are limited by the area. We cannot make it bigger because when die gets bigger, its cost gets higher. The other thing is when we have a bigger area, so we want to optimize the area as less as possible. Performance is the frequency, I know how the current speed. We want to make it faster and faster. Okay, so we want to get much higher performance. And in the power, you want to have as less power as we can because more power dissipation happens. Your die will get hard. You need to have more cooling mechanism on the board. So PPA, these are the three factors that really we want to optimize on our circuit. And in order to support these three goals, each standard cell will have a different version, which I mentioned, water 1, 2, 3. And with different widths, for example, as width goes up, that area gets more. So if you want to optimize a circuit for better area, you want to keep a smallest possible area, then you don't want to use bigger transistors with bigger length, bigger width. And if as the width goes up, okay, your frequency, it will get faster. So I mean, higher width would be good for performance point of view. Okay, but higher width is not good for power. And if you look back on this mass, there is this one is better. There's a capacitance here. So higher the size of these regions, more width, more capacitance will be available here. More capacitance means more current will be flowing there. So overall, circuit will have a bigger capacitance, so you need to drive more current charging and discharging. So overall impact is the power is higher. So we have all these different types of standard cells in our library, and the job of a synthesis tool, job of a physical design optimization tool is to pick these different things, to look for the right standard cells in such a way that we meet our desired objective of power, performance, and area. Of course, there will be situation as you increase the area, power goes higher. But the job of the tool is to keep all those factors at optimum position. And maybe in a given circuit, you are not concerned about the area, but what you're more concerned is the performance. And maybe in certain other areas, you don't care too much about the power because you need a maximum performance. But what happens is, if the power is the requirement, then you want to make sure then you keep the size of the transistors small. Okay, so I think this is enough for today. So we have started getting into a standard cell library. We still didn't touch the layout of inverter. So what we'll do is we discuss the layout inverter in the next episode, and maybe we can go further into layout views and timing views, and how those views are used during physical design optimization as well as physical design verification. So, yeah, that's all for today. Thanks so much for watching, and see you next time. Bye.